1997, 2000, and 2003 respectively. Since 2011, he has been a full professor with the Department of Energy Technology, Aalborg University, Denmark, where he is responsible for the Microgrid research program. From 2014, he is the chair professor in Sandang University. From 2015, he is a distinguished guest professor in Hunan University, and from 2016, he is a visiting professor fellow at Aston University, UK, and a guest professor at the Nanjing University of Post and Telecommunications. From 2019, he became a William Investigator by the William Funding, which supports the Center for Research on Microgrids, CROM, and at Aalborg University, being Professor Guerrero, the founder and director of the same center. His research interest is oriented to different microgrid aspects, including power electronics, distributed energy system, storage systems, hierarchical and cooperative control, energy management systems, smart metering, and the Internet of Things for AC and DC microgrid clusters and islanded mini-grids. Specially focused on microgrid technologies applied to offshore wind, maritime microgrids for electrical ships, vessels, ferries, and seaports, and space microgrids applied to nanosatellites and spacecrafts. Professor Guerrero is an associate editor for a number of IEEE transactions. He has published more than 600 journal papers in the fields of microgrids and renewable energy systems, which are cited more than 60,000 times. He received the Best Paper Award of the IEEE Transactions on Energy Conversion for the period of 2014-15 and the Best Paper Prize of IEEE PES in 2015. As well as he received the Best Paper Award of the Journal of Power Electronics in 2016. During 7 consecutive years from 2014 to 2020, he was awarded by Clarivate Analytics, former Thomson Reuters, as highly cited researcher with 50 highly cited papers. In 2015, he was elevated as IEEE Fellow for his contributions on distributed power systems and microgrids. Thank you all. Now, just I think in the meantime, our chair, IEEE Bhubaneswar subsection, Subhranshu sir has joined. Uh, Hello, Subhranshu sir. Sir, are you there?
Just 1 minute. Am I audible?
Yes, sir. Yes, sir. Thank you, sir. Thank you, sir. So please address the gathering, sir. Thank you, sir.
Okay, very good afternoon. First of all, I extend my thanks to Professor Guerrero. We are really honored to have the man of that height, and really Professor Guerrero is known actively and highly dynamic person in the field of power system and related technologies, who has crossed more than 60,000 citations, and really it's a remarkable contribution to the power fraternity. And I strongly believe our PLS chapter, inviting him, has done a great job, because extending his talks to the spheres of power system and power electronics obviously will help us. So anyway, I'll not take much of time. So I'm unable to see Professor Guerrero.
No, sir, he is available. Hello. Sir. His video is also on.
I'm here.
Oh. Okay.
Maybe your settings are a little different. Yeah.
Okay. I'm unable to see. Okay. Thank you very much, Professor Guerrero. I think you can go ahead for starting the talk.
Professor Guerrero,
thank you very much.
Just have, one sentence. All the participants, please mute your mic. In case if you have a doubt, you please type it in the chat box. At the end of the talk, we can I will read out, or you can also directly ask the question. Apart from that, I request Professor Joseph, can we record this particular session, sir? With your kind. Okay, sir. Thank you, sir.
Thank you. Yeah. Thank you very much. I'm really honored to give this talk with you, and I hope that we can share experiences beyond the presentation. So yeah, and thanks a lot for all your words and praises. I'm going to. Yes. So this is my presentation that I title Microgrids from land to the sea and out in space. Yeah, showing a little bit how has been this evolution of the microgrid research. You can find also more information also in our website of our center. Yeah, right now we use this new one. This is the old one. So you can find a lot of things there, and you are always welcome to connect with us. I want to start with a foreword. This is from John Kabat-Zinn, which is one of the founders of mindfulness. He said, "The little things, the little moment, they aren't little." Yeah, and yeah, this is regarding microgrids and also the way of integrating renewable energy. Let's say in a sense of a small thing. Something about me. Yeah, I was always very curious for electronics from 10 years old. Very active ecologist, and I studied telecom. So I'm sorry if I said something wrong when I talk about electrical engineering, because my field is more indeed communications, and maybe that's why we bring with new ideas to this field. And one of the, I will say, one of the more motivation for me, it's music and creation. So music and creation of music also bring me to create also new products with companies like for instance Salicru. When I was back to my PhD, and also right now still we have projects to develop new things. So for me it's very important that all human beings for me are creators. So we are creators, and that's something very important that we cannot forget, each of us. Failures are also very important in life. For instance, Michael Jordan, he said the key to succeed is to failure. Yeah. So you can see a little bit his career: 9,000 shots missed, 300 games lost, etc. Yeah. So I can see the same on me. I get rejected a lot of projects. Some projects went down, some products could not survive, etc. Something else about the limits. Never say never. Yeah, and I will say something else. Never say it's too late. It's indeed never too late. You can see one example, for instance, about the Bengal tiger. And I believe you in India have this kind of tiger. It takes 10 times to attempt when the tiger is hunting a red deer. So the tiger will fail 9 times. Yeah. I don't think that the Bengal tiger is complaining or getting frustrated or thinking, why me, right? So I think that also we need to learn from the tiger. And now looking at what is the impact and motivation that we have in our center, it's a target going for 100 renewable energy. And this target, I can see, for instance, in Denmark, we have it, and I can see more and more countries joining this target. It's not negotiable. You know, we want to go 100% renewable energy, and we don't want nuclear power anymore. This is not negotiable. We have also 2.7 billion people still without access to electricity, and we need them to have it. Another non-negotiable point. So that's very important. Behind technologies, there are ideas, and we need to stick first with ideas and then implement technology. When I talk about microgrids, many people think that this is about electricity. Yes, it's about electricity, but you can see in other fields how they are also implementing microgrids. For instance, in the field of water reservoirs, water distribution, they talk about micronets. When you talk also about food Also, you can see more and more people concerned that you can consume the food that is produced near to your place, inside your region. So I will say that this concept, this philosophy of living is pushing us to go to a more sustainable concepts. And it's a concept which is more connected with our biology. This is our vision in our center. Try to deploy electric systems or energy systems from the needs up to the creation. Not create needs for the population. That's also something important. Another thing that we try to do from the beginning is to take very visionary ideas to our very non-populated areas. Once we see that this problem is solved, we don't need to go ahead with that. And I have to go maybe back to 2003 when we published the first paper about group controller. At that time, we tried to make a controller that doesn't need any kind of communications. As I was a communication engineer, I was very concerned that communication have a lot of problems. So trying to push for that, I can tell you that this paper got a very bad comments from the reviewers, saying that this is not a power electronics paper. That's maybe for power systems. Right now is maybe one of the more cited in the area. The other one was 10 years after. We defined, also together with Professor Vasquez, the framework of how to control microgrids on AC and DC. And this has been almost a standard. Another important thing was the clusterization. So how to join microgrid clusters together, not only a single microgrid, to produce new electric power systems. And our vision here is also going to develop microgrid clusters for develop new smart grids. And this is the concept now. Our vision came for small microgrids, very limited fault tolerance, probably just pilot plants and automatic operation. The goal was to go towards having smart grids by clusterizing microgrids, so interconnecting them. And this means that we need transdisciplinary research areas, telecom people like me, computer science people, artificial intelligence, people that works also on biomimetics, looking at how the nature has been evolution, coming with new knowledge, complex systems, what we call systems of systems, cyber physical systems, and resiliency. So thanks to that, it was born the new center, the Center for Research of Microgrids in the Department of Energy Technology in Aalborg University. And this was an effort pushing after more than 10 years, together also with Professor Vasquez, to have this vision and to implement it. Some use cases we have are, of course, in more modern places in which more electric cars are appearing. More people are installing photovoltaic systems, and they have plenty of sensors inside their houses. And at the same time, we have places like here, this is a picture from Nepal, but there are many other places in which electrification is needed, and probably also going back to DC. So I want to also thank all our center members, because they are really the pillars of this center and this research, and they are the important ones here. So thank you very much. Here you have a list of the people who's contributing. Now almost 50 people, and all our international collaborators. Also, thank you. Here is a picture of one of our first laboratories. So this is the Microgrid Laboratory from Aalborg University. This Microgrid Laboratory is a cluster microgrid laboratory. So we have a number of microgrids. Each of these setup is a microgrid, and then can be interconnected together. It's extremely important, the safety in this kind of labs. You can see how clean are they. And this is very important because if something happened, the student must, or the people who's researcher who's doing the experiments must push the button, here a red button to stop it. So that's very extremely important. Yeah, you can see here how they are using, for instance, MATLAB Simulink to make simulations, and then they compile it to our hardware in the loop system. Thanks to our system, we have a number of inverters, and then we have also smart meters inside. And you can see here what we can do. This is indeed a power hardware in the loop system. All the components you see here, converters, the smart meters, transformers, switches, etc., are real ones. And what we have here, it's the emulation of generation, battery system, and loads. This allows us to interconnect also multiple equipment in a single point, creating what we call multi-microgrids, or they can be connected in different points, so we can also aggregate them in what is called also virtual power plants, VPPs. This is some pictures of our laboratory facilities. This is our IoT Microgrid Laboratory. It's a demonstration lab. And we have also hardware in the loop systems. For instance, we are also developing the next generation of batteries for homes with Zonen battery, and implementing these kind of things with a hardware in the loop system with Typhoon Hill. So these are our center research frameworks. The first one is, as I explained before, microgrid clusters. Second one is digital twins and IoT systems. And the two more that we have here, and I'm going to present, are maritime microgrids, so ship electrification, ports, etc., and space microgrids, so satellites, moon-based systems, and closed ecosystems. Many people talk about artificial intelligence, but I'm not sure if we still know how our brain works. Yeah, we know that we have three brains. Maybe we have the mind, which is placed in our head with around 80,000 million neurons. And then we have our heart, which we know that we have 40,000 neurons. And then we have our digestion system with 500 million neurons. So the same as a brain's cat, as a cat's brain. So if you identify those parts in which we have a lot of neurons, the mind, the heart, and the gut, you can see that it corresponds a lot with what you in India call the chakras. So there's really a correspondence in which you call energy centers, and I will say that they are neural centers. So I will say that this is really amazing. And of course, you know more about these things than myself. Another important thing is that many people say that we are just using maybe 5% of our brains. And this is not true. We are using 100% of the brain. However, simultaneously, only we can use 2%, which corresponds to 4 watts of electricity. And due to glucose and oxygen limitations, that's only this 2%. However, normally we use similar neural network paths. So that's why sometimes we feel that it's difficult to change. But today we know, thanks to the neuroplasticity, that we can change along the life. And that's amazing because it has been demonstrated that when you have, by changing your thoughts, you are also changing your physical structure of your mind. So all these synapses. So finally, it's like thoughts are changing matter, right? This is something very interesting because in many cultures we know that. And here you have these three levels inside our brain. We have the reptilian brain, which is the more, let's say, basic one, always looking for survival. And indeed, here we have all the control for our daily lives. Let's say heartbeats, body temperature, and so on. All these things are controlled here in this very basic control, let's say. And then we have the limbic brain, which has been developed with the mammals. So everything about feelings and emotions are there. Yeah. And that's why if you want to give love to, for instance, a snake and have it back, it will be difficult because it only have basically this reptilian brain, but it will be more easy if you do it with your dog, right? And then we have the third level, which is the neocortex. And neocortex, it's unique. And I will say that the frontal part of this neocortex, it's the one in human beings, which is really no other species have it, and allow us to go to the future, come back to the present moment, and take decisions. Yeah, so that's kind of a predictive thing that we have here. However, and due to this amount of years, limbic brain and reptilian brain normally take the decisions based on emotions and sometimes survival. And then it comes the rational part with the justification. We feel that the decision is taken rationally, but many times it's not like this, and we know that. Other things that has been studied about stress. In the past, we thought that stress is bad. Right now, there are studies that say, okay, a good level of stress can be good because you can generate dopamine, so increasing learning and motivation, and noradrenaline to pay more attention. So that's also good. However, if stress increases a lot, then fatigue, exhaustion, anxiety, anger, and finally the burnout. So we have to be very careful about the stress. Please take this into account in your mind and your lives. Trust and fear. This is from a paper published last 2 years ago. They found out that the same areas you are using to feel trust are the same that when you feel fear. So that means that you cannot have fear and trust at the same time. It's just one or the other, right? So it's very important. You trust, fears disappear. And then all about empathy systems that has been developed thanks to these mirror neuron systems that also has been developed in the last 30 years. And right now it's almost, we use these concepts in our daily basis. More things has been discovered recently. This is from the HeartMath Institute. Communication between the neurons placed in the heart and our brains. There is more communication coming from the heart to the brain than vice versa. And that's amazing because sometimes I ask myself, who is the boss here? So now we understand many of these things. Many things are coming from the heart. And it has been measured that when you have feelings of love, trust, even hate, those neural networks that you have in the heart are activated and they come with signals to the brain. Yeah. So you can see that's very important when you are in the state of incoherence, what kind of signals can we see? And when you are in coherence, how are the signals that you have? Let me be more explicit. Some people think that heart rate must be constant, and this is not true. Your system, the body is trying to maintain blood pressure constant. And you do this by changing the heart rate. So heart rate must change all the time. And when they told you which is your heart rate, sometimes they are telling you the mean value, right? But you can see here how it is changing. You can see here how is this heart rate when you are in, let's say, frustration, anxiety, worries, irritation, these kind of feelings. You enter in non-coherence between the heart and the brain. Yeah, a lot of harmonics and non-periodic waveform here. However, when you have feelings, positive emotions, appreciation, love, courage. Then you can see how your heart and brain are well synchronized, and then you have almost a sinusoidal waveform, right? And we know also that the heart have an electromagnetic field 5,000 bigger than the brain. It can be measured in more than 2 or even 3 meters. And sometimes we can see how hertz can be synchronized, for instance, between dogs and the owners. And also has been made many other tests, like two lovers together, how their heart rhythms are synchronized, and even people singing together. So I will say that this is really an amazing field. And now we want to see those kind of things, what happened with microgrid systems. Indeed, our microgrid systems are also like our bodies. We have also 3 levels of control, and sometimes an energy management system that is more and more similar as our cortex. So that's also very important. Even though we can see that some years ago it was a huge trend going for DC homes, so saying, okay, maybe we can convert our homes to DC. Right now we have seen that this is not happening, and we know this through a number of projects. However, still there are some of these products. This is, for instance, one of them from Schneider, which is only selling in India, in which they are placing solar panels together with battery systems, and they can transmit power in a distance of 1 to 2 kilometers in the level of 230 volt on DC. And then normally you go inside the houses and you step down 230 volt to 40 volt. And the idea of going to DC also is not new. So also this is from a paper in 2010, in which Professor Kakigano proposed the idea of having bipolar DC microgrid system. So it could be plus, it could be minus. So this is like a 3-phase system, but this is really something very reliable, in which even if you had one failure in one of these phases, still the other is running. And it's very easy to convert from DC to AC just using a half-bridge converter. So that's a very amazing idea, which was the idea to implement in houses, but it was almost never implemented in any house. However, we have, for instance, in Finland, distribution systems in DC working with this idea. And right now, I will show you also another example in an aircraft in which this idea is already implemented. So I will say that that's also a very amazing, let's say at that time was not popular at all idea, but right now has been put it forward in different applications. Yeah. Another idea also here, it was from a company called REBus. The company was entering bankruptcy, so finally this was like an open standard to have DC microgrid systems. The idea was the same to implement this at home, but DC homes was not coming in the market. But I will say that what is very nice here is that they were using the voltage level as the frequency control in AC power systems. So basically, when the voltage inside your microgrid increases, they start reducing the power coming from renewables. Yeah. Exactly like frequency control. Those ideas also we studied years ago with this other project, residential LVDC. And one of the most interesting things was to study also electric vehicle charging stations. And electric vehicle charging stations, you can see that if you go from level 1 or 2, normally you are using the rectifier or the charger inside your electric vehicle. But when you go level 3, you are charging directly the battery from your charging stations. Yeah, this is just one picture from my car, Nissan Leaf, and you can see here the connection in AC, small one, and then this is the big one, we have like 500 volt in DC. Those charging stations, for instance, in Denmark are 100 kilowatt. So imagine that if you have 10 parking stations there, of course, you will need around 1 megawatt. So that's challenging. But of course, this must not stop us. What we need to stop is the way that we have been done the things until now. So, and to create new problems that we will solve later. Amazing things that are happening. Bidirectional converters. In the past, few people was thinking that this is useful. I can tell you that today, because more and more people is working a lot of hours at home, this is really useful, especially when you combine solar panels with electric vehicles, because you can use part of the electricity during the night. And this is a small part of the electricity. We are not talking of huge amount. You can see, of course, this is for me amazing, because you can see a lot of electric and also plug-in hybrid cars recently, which are kind of giving away the all hybrid ones that were not plug-in. You can see here, this was the proposal from Nissan Leaf with this product, Leaf to Home. But today there's a huge amount of companies also selling bidirectional chargers. Yeah, you have 6 kilowatt just for you to power your home. In the past, and I will say that still now, some people are thinking to have stationary batteries at home, especially because when you are not at home, you can still charge the batteries from your solar panels. So creating a microgrid, and this is something that is already available in the market. We can see a huge difference when we start studying microgrids 20 years ago or 10 years ago, in which almost no product was having microgrid functionalities. Now there's no excuse to build microgrids because we have a lot of those products available in the market. When we talk about fast charging stations, of course, we talk about DC, especially when we need to plug those electric vehicles with CHAdeMOS, and this is becoming more and more important. They are also having stationary energy storage systems. We made a project by using flywheels to support electric vehicle charging stations, but also second life batteries are very important here, just to replace those ones who are old for the cars, but still can be useful. And when I talk about electric vehicles, some people think only cars, but also we have aircraft, we have ships, and we have many other trains, subways, and trams that are already working like that. And this is one example of microgrid implemented in an aircraft. This is the Boeing 787. Of course, this is the main propellers are still conventional, but you can see that there's some auxiliary power units which are working full electric with some small wind turbines here creating the electricity and battery systems. You can see here, this is like 4 AC microgrid systems in the level of 230 volt. And then there is 4 more microgrid systems which are bipolar. As I mentioned before, the idea from Professor Cagliano here implemented plus, minus, and 0, 270 volt on DC to support all this demand and connected to a battery system. If we go to the sea, we can see that there's also a huge impact there. We want to reduce more and more the greenhouse emissions coming from the ships. And this is just one example. It was launched 3 years ago by the Chinese in Guangzhou. It's the largest cargo ship with battery systems. This is 2.4 megawatt hour battery. And you can see after this that there's also a large increase of those kind of systems. So going from totally segregated system, like let's say our all conventional cars, that they had segregated the electric part and the propulsion part, Yeah, but this is old-fashioned. Going to hybrid, and then going to full electric systems. And we can see that this is happening with cruise vessels, drilling ships, OSVs, which is called offshore support vessels, also L, and also liquid natural gas carriers. So basically, you can see that there's a number of diesel generators that creates the electricity. Then we have power converters, and then we have our variable speed drivers going to those propellers. This is the main structure here. So here you can see here again conventional ships as our all conventional cars, and how this is having a transition to have hybrids in which we have prime movers, basically diesel to generate the electricity, and AC distribution systems, and then the integration of battery systems moving also to DC. That's very interesting how also all these ships are also moving to DC. In this picture, you can see one of the important things. It's basically the battery systems. This is the power converters. You can see here a couple of diesel generators with the power converters, and then here the connection to the variable speed drives and the motors. Yeah. This is one of the first ones, Queen Elizabeth #2. Number of diesel generators connected to an AC bus, and then from a transformers going to variable speed drives. Good idea. However, it's a single bus, so a small problem that we can have here, it may damn the whole system. So right now, all the ships come with at least 2 buses. So this means that we have one bus connected in the port side bus, and the other is in the starboard side bus. Yeah. So basically, if something happened here, a short circuit, we can open this part, and still we have redundancy here. We talk about huge motors to propel. So thyristors are a very, very good solution here, very reliable, and transformers also are very good and reliable solution. Yeah, I love it. Then you can see also here, this is from a standard of IEEE, and it's really a multi-microgrid system embedded inside our ships. So it's called also Zonal Electrical Distribution Systems, ZEDS. You can see if some short circuit happen, we can open thanks to those bus ties, and still will have surviving the different zones, which are indeed microgrid systems. So I think that this is very, very resilient system. Especially we have to think that there are people on board, and this is really crucial. Nobody's there, no main grid to support this. So it's really a totally islanded system. Yeah. And then the combination between AC and DC has also brought the attention, especially in the industry, to provide also power converters, and to have, yeah, and to manage the energy inside. Yeah, this is another example also of a ship using a multi-microgrid system, in which you can separate on different zones. You can see here number of microgrids. In this case, 4 microgrids. And this is let's say the most conventional one. We have a number of diesel generators connected to a box, and this box is called AC switchboard. And why it's called switchboard? Because it's a number of switches put it inside the board. Yeah. So all these switches are connecting the different diesel generators. Then they go to this kind of, let's say, transformers, and then they have just rectifiers, normally, as I mentioned, thyristor based, which are really good. Normally this can be like 12 poles rectifiers, and then we have the variable speed drives. However, if we want to increase the efficiency, right now a lot of them are moving to DC. So this means that first we rectify, and then we got a DC distribution system. And then from DC, we convert to AC by using a variable speed drive. Maybe you think that it's the same because you have the same number of conversions, but however, we don't fix here the frequency. So this means that this frequency can change according to the loads, and thanks to that, you can improve the efficiency. But of course, this depends on the mission you are using. You can see here, this is the converters from the starboard side, and this is the converters from the seaport side. Yeah, always the ships are berthing in the port with the same side. Yeah, this is something we need to bear in mind when we are also building the electric infrastructure of the ship. Then this was a concept from Siemens, and after a concept comes from Siemens, automatically ABB say, okay, I have another idea. Why don't you put the converters close to the generators and close to the motors? Even you can embed them inside, so you can reduce the losses, because normally you have long lines. However, this means that you will have to increase the voltage of the DC distribution line. And if you increase the voltage, you can imagine that those tie breakers and all the switches and protections will be compromised. This is a problem. Maybe you have an amazing switch in a laboratory, but you know, when you go to the maritime industry, you need at least 20 years of proof of this element that works in the field. So we cannot come and say this is maybe nice. You can see here the long distances that you can have between your generation and storage systems and your propellers. Yeah, and this is the reason why some of these ships are moving from AC to DC. You can see if we fix the frequency, losses will have, let's say, a minimum in certain point, which corresponds to certain load. However, if we change the frequency, you will see that this minimum goes to another place. If we want to have this almost constant, the best way is to change the frequency according to the load. So you will select this or this other curve according to how much is the load. Yeah. So that's nice. Of course, we have to bear in mind the losses that we have here. So that's why it's not always the best solution. It's just one of the solutions. Another idea, it's because the efficiency of the diesel generator depends on the frequency, we could also make our bus, our main bus, on a variable frequency, which is something that we people in microgrids like very much, to change the frequency, right, according to the loads. But of course, this may attempt how the transformers are being used, maybe the efficiency, maybe some harmonics or interharmonics can appear, and maybe transformers are not designed for that. So this is something that still is under development. Even though the first studies show that you can have up to 6% of increase in annual savings for very large cruise vessels. Yeah. And another thing that we can do is to recover also the energy when we are slowing down our ship. So like a regenerative breaker. This is something that if some of you have also an electric car, you can see when you are braking, you can charge the batteries. So this is something that we can do also with our ship when we are berthing. And this is just another example with a platform support vessel, you know, because we are building a lot of offshore wind recently. For instance, in Europe, we have the plan of building 300 gigawatt in the next years. You can see that also Asia have amazing plans for that. And that's why also we need vessels that are also more kind with the environment, right? It doesn't make sense if we are going to build offshore wind and we are going to pollute a lot the area. So we have to be consistent with that. And you can see a lot of these platform super vessels, how are also they shifting from AC to DC to improve the efficiency. You can see here, this is a comparison. This was made in Singapore, I believe, from Rolls-Royce Laboratories. And they make a comparison between an AC ship and a DC ship. Those were the losses. You can see how how flat are the losses when we are using DC, while when you are using AC, it's very variable according to the load. And another example, this is another kind, this is an OSV, this is the offshore supply vessel, that's from Norway, the Viking Lady. And in that case, this vessel from Barcela, they integrated also fuel cells. I want to tell you that also fuel cells are coming back, and you can see a lot of hydrogen applications here. Very, very exciting. Yeah, it's not a small one. We talk about 320 kilowatt fuel cells to support a 1000 volt DC microgrid system. That's basically for auxiliary and to help the tunnel thruster to be supplied, and some of our hotel loads also. Exciting things also about what we call dynamic positioning. Many times we need that our ship or vessel have a fixed position, even though if we have a lot of force and motions, wind, maybe the sea becomes brave. So we need to sense using GPS systems, gyro flux gates and anemometers, put it inside our systems and try to make, for instance, this is a semi-submergible rig in Norway. And you can see it looks very nice, normally with the keyboard and probably a joystick. Yeah, this is very 80s gamer setup, but this is how it looks like. This is from a dynamic positioning system in Brazil. And this is basically the model, no? So you have the vessel, you got the position, heading measurements, and then you have the wanted position. You need also the wind model, probably also sensors from the sea, and then how we can integrate in the thrusters. Yeah. Some ideas has been implemented. For instance, this is based on a Kalman filter idea. And you can see that really the system is really complex. Yeah. And you can see that also huge amount of power needs to be used. So that means that more than energy here we need pulses of power, and we have been also shown that you can get also a very flat response. Yeah, this is another example from another offshore support vessel. Yeah. And finally, if you compare the power demand with other, let's say, services of the ship, it needs almost 37% according to this study of the time, and this is a demand of around 2 megawatt power. So it's really taking a lot of power. And you can see here the marine configuration of one of these vessels. It's really amazing because you use a lot of parts that are normally used for conventional electric power systems, like IEDs for protection, and also using 61850 standards. Yeah, I will say that this is very nice. So I will say that there's a lot of work to do from people that works with electric substations that can give also ideas for electric ships. Yeah. And you can see also going to small ships like yachts, they are coming also with this idea. This is a very early yacht. This is in Slovenia, in Europe. And you can see photovoltaic systems and a hybrid electric system. So you have a gearbox with an electromotor and a generator. And then you can charge the batteries from the dock. So once you are in the seaport, you can also charge it from the PV panels, and you can work in hybrid mode as well. Also, we can see here in Denmark how our ferries are becoming hybrid more and more. So also with the ideas that some of them are becoming also full electric ones. And this is one of the examples. They took out 85 tons of motor and then putting 50 tons of batteries in. and all the control and power electronic systems, becoming the world's largest hybrid ferry fleet in the world. We have here in Denmark. Another interesting project we developed together with Taiwan is to have the first hybrid electric ferry in the whole Asia. Yeah, it was 4,500 passengers per day. And we took out all the motors, old-fashioned motors, and put just power electronics from Visedo. Right now, this company is absorbed by Danfoss, so Danish company. And we implement also a battery system, 100 kilowatt hour, to make a hybrid system. So you can see that this is really a DC microgrid, coming with elements like rectifier, DC-DC converter, which is indeed also a three-phase inverter with like 3 buck boost interleaf converters. And here we are creating 750 DC volts. So I will say that this is really amazing how a DC microgrid can be implemented here. Those batteries are not conventional batteries, are approved to put in a ship, and they come from a Holland company called Superb, but we have many others here in Europe, more and more. So we expect more ferries becoming electric here. We also made a study together with Poland about power quality issues in shipboard microgrids. So right now there's classification and rules standards, and there is maximum voltage deviation and frequency deviation and maximum THD also. Different as it's defined in distribution electric systems. They have their own standard. So we took Horizon 2. This ship goes twice per year to the Arctic Sea. Here you can see the ship, beautiful one. The engine room, the control board, diesel generator, and the pump. So here is the electric system. Yeah. What we saw here is we start to study where the voltage well balanced, the currents, and so forth. So you can see the whole electric system. When it comes with a small imbalance in the grid, very, very small, for instance, 1.5%, which is very acceptable, you can see the huge imbalance that are created in the currents that goes to the bow thruster. So it's very important for this kind of systems to maintain the voltage balance. Other things that are happening in electrification of ships, when a ship is coming to the port, many times they start the diesel generators because they need, for instance, to start the freezers, especially if it's a cruise vessel with a lot of freezers. They want to maintain the food. So that's why in many ports right now we are connecting what is called also cold ironing. So connecting from the port side and supplying electricity to avoid this annoying, let's say, contamination. Yeah, and you can do this through direct connection to the grid, and this can be supported by stationary battery packs. This is very well done in many places in Norway, especially for charge ferries or direct connection. One of the possibilities is also having a DC microgrid system inside your port, coming from medium voltage, rectify, and then a number of inverters, because depending on the vessel, they come with 50 Hz or 60 Hz of frequency. And it's very important that is the port who synchronize with the ship, not vice versa. Otherwise, due to the lack of inertia, you could have heavy spikes flowing between the port and the ship. So that's why it's so important to install inverters in the seaports. And the same thing we can see with the cranes. Even though a lot of cranes are electrified, some of them still, they are supplied by diesel generators. in ports, creating more and more CO2 emissions and contamination. So that's why what we proposed is to say, okay, why not when we are lifting up containers, we need energy, but when we are lifting down, our motors are working as generators. So we could use this energy instead of burning in dummy resistors. We could reuse it for other cranes or internally inside our seaport. And this is the idea. Many studies shown that at least you can recover 40% of the energy, even 50, depending on the study and the technology that you are using. So I will say that this is amazing. And the other thing is that you can reduce a lot the peak of consumption in the seaport. Another thing is about what happened with offshore wind. We have seen that there's a lot of things happening with seaports and vessels that are going to offshore wind. But also offshore wind farms are having ideas, getting ideas from microgrids. You can see that we are really going offshore globally, more than 3,000 megawatts already installed in the world. And you can see also that this was a vision of a dream. So first it comes a dream. This is a very old picture in 1977. It didn't exist any offshore wind farm, but this was an illustration. And then it comes the reality in 1991 in the south of Denmark, the first offshore wind farm, only 500 megawatt. Yeah, we still love small things in the microgrid field. So I will say that this is really amazing one. And then after this, the size and the power of wind turbines has increased dramatically. You can see the last ones surpassing 10 megawatt probably. And in islands like island of Taiwan, you can see ambitious offshore wind farm plans, like growing to 10 gigawatt in the next years and being totally disconnected from any other power system. However, we can see also that this has been also a problem sometimes. For instance, this is one example of what happened in UK 2 years ago in the summer. It was one of the combined cycle power plant station that shut down. Frequencies start to go down, and then the offshore wind farm get tripped once they see that the frequencies go down. And then we are thinking, if we are going to integrate more renewable energy, we need them to also work as a synchronous generator, more like part of the grid, more contributing to the frequency support. And this is one of the ideas that we have in our team also with this project, which is called WindFlag, in which we are supporting Turkey to develop new ideas for their offshore wind strategic plans. You can see that here the idea is to implement, again, 3-level controllers. So having local controllers integrating virtual inertias, secondary controls to control the voltage and the frequency when the grid is weak, and also to help the wind farm to restart, to have black start operation without using, for instance, diesel generators. This is very weird, but it's true. When you have to have a reparation on the subsea cable, and then you have to, for instance, restart the offshore wind power plant, many times you are using big diesel generators that are polluting the area to restart the offshore wind power plant. And this is a little bit, it's totally against our idea of having a more clean resources. And then we have the tertiary control, which are going to coordinate with the existing hydroelectric plants and probably adding more energy storage systems. So this is an amazing project, and you can find more information here in our website. And you can see also that wind farms, when you talk about multi-terminal HVDC systems, they are also using groups. So a lot of the ideas that we have been developed for many years in microgrids are being reused in wind. And you can see here also the hierarchical control, which I will say that is kind of, if we go back to the brain, the 3 levels that I explained. Primary controller, this is more impulsive, let's say, yeah, reptilian brain. Secondary control layer, limbic system, and tertiary control, more connected to this neocortex. Right now, it has been also implementing and adapting to offshore wind power plants. So we are doing these kind of things. And of course, we are testing a number of controllers here to have not so much grid following systems, which we know how they work, but having grid forming wind turbines, because we want them to support frequency and voltage in the system. Yeah, I'm going to skip a little bit this. And this is why we need microgrid technologies when we go offshore. We use fully equipped converters, 4-type wind turbines, so all the power goes through the converter. We have the possibility of islanded and black star operation. We have also the virtual inertia, voltage and frequency support, as I explained you, grid forming inverters, and then maybe the need for energy storage system. Yeah. So this way we have the next generation of offshore wind farms, which are coming, and they should be finally the main producers here in our systems. Yeah. You can see also a lot of works, like this is from another project. It's an European project in which they translate also some of the controllers we developed for many years, also for offshore wind power plants. Yeah. So you can see very similar controllers, like having frequency controls, droop controllers, and hierarchical controls right now embedded also in wind power plants. The next step, it's going to be to have control architectures when we have a number of wind power plants, which can be more centralized, more distributed, or we could have also hybridized, so having some part of the controllers distributed and some part centralized. This is something, another heritage from microgrid systems, in which multi-agent systems has been also developed for decades. Yeah. And now we move to the last part of the presentation, which is basically space microgrid systems. Yeah. We finalize with the Earth, let's say land, sea, and now we go into the space. When we go to the space right now, for instance, we are collaborating with a very good company, ComSpace, placed in Aalborg in Denmark. And they are producing what we call cube satellites. And those satellites, you can imagine that we have a number of communication systems and payloads. And finally here, what we are talking about is to have solar panels, battery systems, and finally DC microgrid systems. So you can see here one example. This is lithium-ion battery systems. And then we have converters. It's like a boost converter, and then bidirectional converters connected to battery systems, and then a number of voltages to supply the loads that we have here, like gyroscopes, magnetometers, etc. Yeah, and of course, all the communication system. One of the important things is that in a satellite, we have eclipse every time. So once we just turn one of these cycles, we get an eclipse. Yeah, you can see that the satellite and the sun, it's here. And then during this period, we don't have sun, and then we have full sun here. So that's very important. We have to size the batteries according to this eclipse area. And another important thing is that we can also have cosmic radiation. So this means protons impacting our solar cells. So that's why we are studying how is the degradation. And then another important thing is that all about electronics, For instance, if you have a microprocessor, it can be hung up. So this means that your microprocessor is not useful to control your power electronic systems. You need to control them through analog electronics. So analog control is back, thanks to go to the space. And then microcontrollers are just using as a supervision. This is another example from a CubeSat in Finland. And in that case, what they wanted to measure is the sunstorm radiations. And thanks to that, they use this plasma break and this particle telescope system. So you can see them as the loads for that. And they were using basically gallium arsenate solar cells in some of these parts. And also they were using 4 separate MPPT chargers. And you can see here how this was working. So this is the 4 MPPT chargers. And as I explained you before, the microcontroller is only using a supervision, but here all about control must be done by analog electronics. So here you can see also all the subsystems, the particle telescope to be supplied, the electric power board, the camera, magnetometer, all about communications, also radio, and so forth. Another example, everybody knows that one, is the International Space Station. We are talking about 36,000 solar cells here integrated in around 300 kilowatt system. And you can see here how it works. We have battery systems. We have these photovoltaic arrays, as I explained before, these 36,000 solar cells. And then we have all these power converters interfacing. This is what is called also the primary power system, which is along 133 to 177 volt. And then one conversion unit going to 120 something volt. And then we have here the secondary power system. Yeah. And then we have a number of existing loads. And then we have the payloads here. So here also is really interesting how this system, before it was designed on AC, before 2005, after 2005, all these systems were replaced on DC. So it's clear that DC microgrids are going to the space, even with large systems like this one. And this is what we are seeing here. Analog electronics for the control is very important also. And special degradation models for solar panels or batteries are needed due to the cosmic radiation. And now another project we are doing is to develop lunar-based microgrid systems. It's becoming exciting because you can see that recently NASA said that in 2024 they are coming with a moon mission. Also, we have same here with Amazon. Yeah, SpaceX also saying that they want to land the Starship in the moon before 2022, and then having cargo with human landing in 2024. Also the same here with JAXA. The Japanese are also coming with the same idea. And also China, of course. So right now we know the situation. We can see how the moon is becoming exciting. And this is a little bit about the lunar-based construction periods in which we go from non-state, from human beings, till 3-4 personnel during 4-6 months. Phase 2, 10 personnel 1 year. And finally, more than 100 personnel with unlimited duration. Yeah, I will say that this is a little bit the idea for the next 15 to 20 years. And we look at lunar-based systems as a power system with power generation. Lots of opportunities about solar cells. Some people are proposing nuclear fission. We are not fans of these kind of technologies, to be honest. And then we have also electrostatic charge. Because of the electrostatic charge that we have in the moon, maybe it could be possible to generate electricity, but this is still under developing in laboratories, so not available now.
Professor Joseph, you have been muted. Can you please unmute?
I think in the Microsoft Teams itself, you can unmute. Yeah.
How it is now?
Now
Yeah,
it is.
fine.
Thank you.
Sir. Yes, sir.
Oh, sorry.
Yeah, it is just maybe 10 seconds before. So far, it is fine.
That's good. 10 seconds.
Yeah, when you are discussing that nuclear one.
Okay. How we can just continue this like this?
Yes,
No.
sir. Yes, sir. From here only.
If I do this, I will start from the beginning.
Yes, sir. Power generation completed. Yes, sir. You can start from here.
Sir, yeah.
Perfect. So then, yeah, there is some people trying to push for nuclears. We think that is hazardous. We know that complex infrastructure, more weight, and of course more expensive. So for us, the winner is clearly solar energy. Yeah. So space is solar energy and DC microgrids, clearly. Not hazardous, convenient, very light when you compare with other technologies, and it's already tested for many, many decades. So you can see here just one example in which we consider the lunar-based power system. We consider the power generation, storage, loads, and the power management and distribution. You can see here the two faces of the moon, the near side of the moon and the far side, with possible locations. And some of the craters, for instance, this is the Peary crater in the North Pole. And one of the things is that you have low declination angle of around 1.5 degrees. And this means that we have little variation in solar elevation. So it's almost all the time perpendicular. And we have continuous variable through all the year. So I think that's also very nice. However, we have challenges. We have steep terrain in the polar regions. And we have transition to sunline regions, more than 15 days in high terrain and less than 15 days in low terrain. So that's also something to take into account. Also, we have twice per year, we have 5 hours of eclipse, which we need to also take into account because we're going to be very highly dependent on this solar energy. And then we have some polar regions of interest. One is the South Pole with what is called Shackleton crater. A lot of work has been done with that. And then in the North Pole, we have the Peary crater. So we basically focus on these two craters. And in the first one, the Peary crater has few locations which receive continuous sunlight. And for instance, if we could put towers of 100 meters, it may reduce the energy storage system requirements. So this is one possibility. The other is with the Shackleton crater. It has most illuminated locations, and the average radiation is around 80%. So it looks also very interesting for installing solar panels there. So we can see that this power generation, it depends a lot on the location and the site. Then about the energy storage system, we have to consider in size according to this illumination and darkness. And we have requirements like high specific energy. We need more than 500 watt-hour per kilogram. Long life, yeah, more than 5 years, 10 years or more ideally. And long cycle time as well as specific power. So that's also very important. Right now, the two technologies we have available for that are battery systems and also regenerative fuel cells, RFCs. So you can see also how hydrogen is also going probably to the space, and this can be also thanks to the discovery of water in some parts in the moon, and also probably if this can be extrapolated to Mars someday, right? Lithium-ion batteries, absolutely. You can see that the same thing is happening here in the Earth. And this is just one example of 1 month illumination conditions in the Shackleton crater. So we have some areas in which they are pretty much illuminated outside the crater. Yeah. So that's, again, very much dependent. And then we have here the loads, and these loads, we have the crew habitants, those future habitants that we will have. Also, we expect to have laboratory and exploration inside. And then we will need in situ resource utilization, right? Because we will have to depend more and more of our own resources in there. So there is also study done about how much is the power that we need per habitant there, around 5 to 10 kilowatt per person. And then the communication systems that we will need, charging stations also that will be needed, etc. And this means that also we know that in the Earth we have satellites and communication systems, and this can help us with the control with our power systems. But if we go in the same direction to the moon, of course we can have intercommunications between the Earth and the moon, but we expect that they will have their own satellites. So new satellites are going to be placed there, and they will need to be synchronized with their own stations. We cannot make them depend on the communication with the Earth. So basically, we expect that those satellites are going to intercommunicate base stations inside the moon, not only with the Earth. The other thing is, like, thinking about a single microgrid. It's fine to start, but we expect to have multiple microgrid systems which can be placed in different parts of these craters and can help us with improved resiliency. So here are the specific objectives that we have for that. And we have, of course, to design energy management systems that can cope with that. That's the example we are working right now with the Shackleton crater, in which we are having a number of photovoltaic systems. Probably one of these systems to support the lunar habitat. The other is for laboratories and charging stations. And the other is to develop your own resources here. So we will need also the communication systems to synchronize with these satellites, the moon satellites. So we can have a number of zones, and we expect to interconnect them, those microgrid systems, between them, forming multi-microgrid systems. Yes, and I want to finalize with another project we are doing with the European Space Agency. And this is using ideas from the control of microgrid systems to be applied to control of spaced closed ecosystems. As I explained before, we are thinking on the moon, and in the moon we will need also to develop our own biosphere. So that means that at the beginning, we will have very closed ecosystems. We will have to supply oxygen to these habitants, and we will have to do it through some biologic systems. We have to think that we are biologic people, so it's not like I'm just working with equipment. It's very important to have this connection, and you can see how we are developing these things here with a laboratory in Barcelona. We have the people, the habitants in the moon, and then how you generate waste, and then from this waste, and using a photo electrophic system, you can generate the minerals for the nitrification part, and giving also CO2 for higher plants. And then this nitrification system will go to microalgae and to higher plants, which generate oxygen. And this oxygen can go also for the population. People could eat these higher plants and these algae. They generate as well water and some other food that cannot be eatable, but can be used again to put it back for those bacteria who will close again the system. When you look at this kind of system in which we have nitrification compartments, photobioreactors, the plants, and right now our crew compartment members are rats. We're making this test with rats. It's really a closed loop system in which we try to fix the oxygen in a very tight levels. Yeah, right now we know that it's very important. If you know about corona ill people, they are trying to support with very tight oxygen levels. And of course, this is very complicated because this kind of system is highly non-linear and with high order. We talk about hundreds of state variables here, so it's not so easy to control. The first time we saw this system, we thought this is kind of a microgrid. You know, it's a closed ecosystem. Nothing is there except the sun. So the sun is helping for the photosynthesis of these plants, and all the other system is like we are storing oxygen. So kind of similar as what we are doing with energy storage. We have some microbial fuel cells, which can be assimilate to hydrogen fuel cells. And this photosynthesis is something similar as what we do with photovoltaics, right? So taking this into account, what we did in this collaboration project is we developed the same hierarchical control structure in our facilities to control this pilot plant by using a 3-level controller. So the same way that we are controlling microgrids, we are controlling closed ecosystems here. This was our initial idea. This is right now already published in a magazine, the Industrial Electronics magazine. If you want, I can hand you the copy. And here the idea is that the primary control, which was, you know, this reptilian brain, it was used for control active and reactive power. Here what we control is the mass flow inside the closed ecosystem. The secondary control, which is this limbic brain of our brains, is to restore voltage and frequencies in microgrids. Here what we do is to do corrective actions for the prescriptions and flow dispatching. And then we go to the tertiary control, which is this more rational brain, right? The neocortex. In a microgrid we use for energy management system. And in that case, we are using like in an operation management system in which we try to optimize the setting points. So I think that this is really amazing how we can control a bio system by using ideas from controlling electric microgrids. Yeah, and here there are some results. It's a little bit complex to explain right now. We have the oxygen tanks, we have all this system, and finally what we try to do is to obtain oxygen levels near to 21%. Yeah, and you can see how all the system is working in terms of light also, and here we have also the oxygen tank levels. which also has been a lot of problems to size it in a similar way that happened with battery systems. So thank you very much for your attention. And I would like to finalize my talk with this that Edison wrote in 1931. He said, "We are like tenant farmers chopping down the fence around our house for fuel when we should be using nature's inexhausting sources of energy. Sun, wind, and tide. I put my money on the sun and solar energy. What a source of power. I hope we don't have to wait until oil and coal run out before we tackle that." What ambition, really ambition words of Edison. Thank you very much.
Thank you, sir. Thank you. The floor is open for questions. Anyone who wants to ask any query, any clarification, they can unmute themselves and ask.
Hello, everyone.
Hello.
Just I want to thank Dr. Joseph for your excellent presentation.
Thank you very much.
Really great presentation and very informative. Thank you very much.
Thanks. Thanks for your attention and words.
Good afternoon, everyone, if I may.
Sure.
Good afternoon, dear Professor. I hope you're doing good.
Yeah, thank you. I'm very good.
Thank you, sir. Okay, so there was a doubt which I need to clarify, and it is like, what could be our preferable approach in case we need to solve instability in any multi-agent cooperative system due to fading of due to the fading effect? How can we get rid of that? Any preferable approach to get rid of instability due to fading?
Yes, I understand that multi-agent system has been developed for many years, and it's very useful, especially in robotics and many other areas. And my experience is that it works very well when you have a field communication. So for instance, when you have CAN buses or any other conventional ones, it works very well because, for instance, when you work with CAN bus, you put one data there, automatically all the units will see this data. So we implement this idea in a UPS system, and it's now a product in the market. However, when you have wireless or you have internet or you have more hazardous communications, then it's difficult to make them stable. So I would recommend that in that case, at least you centralize some part of the algorithms and you can help on the supervision, because it really have a lot of problems, especially when we talk about commercial products that you cannot fail. When you talk about a distributed UPS system, is to support, not to be too dependent on the communication. So I will say that this is one of the things. And the other thing is if you have a multi-agent system and you see that, for instance, communications are failing, you should have a B plan to make your system to work with less performances, but still like a total distributed system. So you allow the system enter in a mode in which you have less performances, but still it's kind of when you are working with resiliency. Normally, people who work with resiliency, they have an event and you go to a lower performance, but still this lower performance adjusts to the performance that you can survive for several times, and then you can go back to maybe an intermediate state and then go back again. So yeah, probably you can sort it like that.
All right. Thanks a lot, sir, for the answer and for the beautiful presentation. I just loved it. Thank you, sir.
Thank you very much, Gaurav.
Professor Joseph, this is Dr. Chandrasekhar from IIT Bhubaneswar. I have two questions. The first question is that when you have mentioned that we are using a fuel cell in shipboard systems. So what kind of fuel cell it is and what is the fuel? Is it something like that solid oxide fuel cell where doesn't have any kind of reactor, or to ensure the reliability, are we going to have some kind of hydrogen storage?
Yeah, it's a very good question. There are several technologies. The one that I show here, it's like you have nitrogen, and then through the nitrogen, you have a reforming, and then you can, let's say, support a fuel cell. Normally, these fuel cells that you can see now, they are PEM fuel cells, but some ideas on SOFC fuel cells are already right now in development to put in the maritime industry as well. So, but as you know, the temperatures are much higher, so you also have to think about how you place this in the ship.
And my second question is that this ships, we are basically hybridization of the shipboard power system is going on. So we are going to use batteries. I understand from the presentation, the batteries as the secondary source, or maybe at the beginning we are going to use the battery to support the engine. So how these batteries are really being powered? Is it something like that on the top of the ship? We are going to have the PV system and that is going to power the battery, or anything else? The arrangement is what kind of arrangement we are going to have in case of hybridization of the shipboard power system?
Yes. First, it's not only hybridization. We have already full electric ferries. For instance, there is one in the south of Denmark, and many others in Norway. So we have full electric ferries already. Yeah, I can see more coming. Recently in Spain, I saw also some of them, even tourist ferries. So the point is more than where you put the battery system is, are you sure that you can get the battery system well cooled? Because if you are using lithium-ion batteries, we saw that, especially in the case of Taiwan that I present here, if you don't maintain the battery system because this was lithium-ion, it needs to be around 25 degrees. If you put this, the temperature in a higher temperature, let's say, I don't know, 40 degrees, probably in few years, you will just damage them. So it's more like you have to design the cooling system. Talking about retrofit, once you remove all these motors, etc., you have a lot of space. The problem is this space having the appropriate cool system? Some people even put the batteries, as you mentioned, a little bit higher to allow them that the air is flowing and so on, but you have to design, and it's not always so easy. So it's part of the retrofit challenge, as you mentioned. Yeah. So one thing is the retrofit, so having all vessels and convert it to hybrid, and the other one is to design new vessels. But we have so many vessels we need to retrofit that is really a way that we collaborate with the people who are working on thermal and who are working on mechanics to place it in the best place of your ship. So it's an engineering work indeed.
Thank you, Professor Joseph.
Yeah, thanks.
Well, Professor, this is Tripathi, A.K. Tripathi from Bhubaneswar. I just wanted to ask a general question. You mentioned that in some places you are preferring to go for analog controls and analog wiring, and preferring it to digital control or software-based control. Are there any sensitive areas where you are having the main control analog and supported as redundant digital control, or it is entirely analog? And which are those areas?
Yeah, especially is in the when you have something, let's say, in the Earth, it's not a problem. But when you have satellites in certain levels, you start to have cosmic radiation. So then this means that your microprocessor can be hung up. This is due to a phenomena which is called latch up. The phenomena of latch up is like the protons are booming inside the IC, and then these IC, you have a lot of CMOS, and then these CMOS, you have one of the two transistors get latched, for instance, 2+ VCC, and then the microprocessor is hanged up. So this means that what we need is that all the fast controllers, which are controlling especially power converters, can be based on analog electronics. So this way, you will not have problems with the latch-up effect. While, for instance, what is the energy management system or the power management system of the satellite can be placed in the microprocessor, because it's okay that you have latch-up problem during some time and then you reset it and then you can continue working. But the let's say fast controllers, they cannot stop. That's why we develop them with analog electronics. So then, of course, if we think about a satellite, it doesn't matter where it is. When you have since you will have cosmic radiation, you need that. Indeed, this cosmic radiation even is very bad for the human beings because it can produce you cancer. So all these places in which it should be human beings, they normally shield for them. And this is the same effect for electronics also. So it's bad for us, but it's also bad for digital electronics. That's why all these circuits are going to analog.
Okay, nice. Thank you. Thank you. Another small question is that the microgrid actually came, let us say, within the last decade, and all these power supply source, battery support, and all these things were present earlier also. The control levels of control. We simply didn't call it microgrid principle. Now you are saying that we are using microgrid principle in controlling so many things in the land, sea, and is it something you are now trying to make a microgrid term more attractive for public consumption, so that you are telling that all other controls are following the microgrid concept and principles, or it is vice versa?
Well, the point here is like, especially you can see this especially in the wind power area. If you take a look how it was working the wind turbines in the past, it was more thinking that you are always connected to the grid, supporting with power and so on. At the same time, in parallel, in microgrids, we always need to support frequency and voltage and have grid forming converters. And this has been done in the last 20 years. For the last 20 years. Right now, people from wind power, they say for the first time that they need grid forming converters. So some of the ideas in the control of microgrids right now are being translated in many other areas. That's why I'm saying that this is moving some ideas from the control of microgrids to other places.
Okay, thank you so much for clearing it. Thank you.
Yeah, thanks.
Okay, thank you. Is any more questions? If not, I'll take this opportunity also to thank Professor Joseph, and also to introduce to the members about IEEE PLS. It is a 2 minutes presentation. I hope you can see my screen. I hope you can see my screen.
Yes, very clear.
Yeah.
Yes,
Okay.
sir. Yes.
Yes. So, as a chair for this IEEE PLS Bhubaneswar and Kolkata joint chapter, I want to introduce you to the Power Electronics Society. Most of you have already known it. It is basically a non-profit organization, and also it has been established in 1987. And currently, the 10,000 members are there worldwide. And current office bearers are Professor Lucian Chang. He is the president for 2021 and 22. And the immediate past president and nomination chair is Professor Freddie Blabjerd from Aalborg University itself. And we have our senior and past president and long range planning committee chairman, Alan Manoth. These are Other office bearers, I want to concentrate more on the benefits that this IEEE Palace Society will be giving. It will give an access to all the IEEE Power Electronics magazines. Online subscription will give you to transactions on power electronics and Journal of Emerging and Selected Topics on Power Electronics, and also all the sponsored conferences. Even in 2019, IEEE under the Palace has started an open access journal of power electronics. And other benefits includes conferences and workshops. Especially there will be a discount in the registration on conferences, symposiums and workshops. You can be a part of the technical committee. You can actively participate in this one in various committees that are available. Also, we have a resource center, a multimedia online library that is free for all Palace members. Apart from that, the other benefit is networking, as Palace has 211 chapters worldwide, which includes professional and student branches. We also have flagship conferences such as EPEC and ECC, which is goes in 3 versions, that is North America, Asia and Europe, and ESPEC and COMPEL and PETG. So you can be also a member participating in technical committee, conference committee and chapters. Palace also encourages in women in engineering events and social gatherings and mentorship events. You can have a very good networking once you become a member of this particular society. And for students, there is a discount and 50%. The code also is there. And currently, these are the distinguished lecture programs. Any of the chapter we can introduce. Recently, we have also called Professor Birjan Singh from John Deere. Just a couple of weeks back, we had a distinguished lecture. You can also submit a request by completing the form. This can be shared to you. And we have other educational and student activities which can be seen here. You can participate in IEEE Future Energy Challenge, which is an international competition for innovation, conservation and effective use of electrical energy. We also support, as a Palace member, you can be a student travel grant, mentorship. And the last one is very useful for IEEE Palace PhD Thesis Talk Award. It encourages the recently completed PhD students to make a video up to 3 minutes on their PhD projects, showcasing their research achievements in academic and industrial fields. These are the other standards. And yeah, we also like Palace is also having an IEEE Transportation Electrification community. So we request you to join IEEE Palace today and be connected to the ultimate source of power in your industry. You can contact any of them. These are the office bearers currently. Thank you. Thank you. Yeah, Dr. Chandrasekhar, you can propose the vote of thanks.
Yeah, if no questions, it is my pleasure and honor to propose a vote of thanks to Professor Joseph M. Guerrero. In fact, it is really amazing talk, and it is a fascinating talk. Altogether, it has started from the fundamentals of the microgrid. And at the beginning, the discussion was on how the brain system works, and that analogy, how it was drawn to the electrical system that are existing on the ground from the land. And there the discussion went on to the sea, and we had a discussion, and finally it just landed on the moon. So really it is a fascinating and it is a very knowledgeable workshop, and I'm sure and I strongly believe that all our participants got benefited from this talk. And all of them have taken one or other research area. In fact, personally, I should thank Professor Joseph for sharing his knowledge, and I have taken 2 to 3 things that I can continue with my research, and I strongly believe that all the participants also are feeling the same. So with this, I thank Professor Joseph for sharing his knowledge and sparing his valuable time. And I thank IEEE Bhubaneswar subsection and IEEE Kolkata section for giving a chance to host such a eminent personality in the field. And in fact, I have my personal appreciation to Professor Joseph, being a BS in telecommunications, and later on MS in electronics, and finally PhD in power electronics, and doing an outstanding and commendable job in the field of power electronics and the microgrids. and that too finally is just venturing in the biosystems. So from wholeheartedly, we convey our best wishes and best our regards and thanks to Professor Joseph. Thank you, sir. Thank you very much.
Thank you very much. Thanks for all this event. And I think that it's very important. Always keep in mind what the lemma of our team, you can see in our t-shirt, microgrid seriously affects your brain. So here you have an example.
Yeah.
Thank you.
Sure, sir. Thank you.
Thank you.
Thank you.
Thank you, sir.
Thank you, sir.
Have a nice
Thank you, sir.
Thank you, sir.
Thank you.
Thank you.
I thank all the participants also for joining the talk. Thank you.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you.